So, okay. So the thing is, I'm for the first time coming this university. So maybe it is for 2 slides for where I work. So this is actually here. So this is the city, Calcutta, like roughly around 300 years old, and very close to the sea, around 90 kilometers, 90 to 100 kilometers. And this is our university, where my office is somewhere inside. And this university is roughly around 200 years old. Our department is roughly around 100 years old. And this is the quite, too big city. Maybe you can compare it with Paris, maybe, I don't know. And now a bit of the history of the department. So our departments actually, even if quite younger than the old university in Europe, but somehow still managed to get some textbook results, which are now included in the textbook. So they are kind of important. So this is Professor S.N.Bose, who has known for the research in microwave radio research long back, 100 years back. And then maybe this is, he's more popular, C.V. Raman, maybe you have heard of Raman effect, various textbooks. So he actually taught in our department 100 years back. And then this is M.N. Saha, Meghnad Saha. His research is known for the Saha ionization results in astrophysics. Then S.N.Bose, of course, this is bosons are now everywhere. And then this is younger. He is a good teacher also, and very good scientist, in a sense that he has important contribution in general theory of relativity. So his named equation and aka Rayleigh equation, which comes just, importance-wise after Einstein's equation in GTR. So this is kind of brief introduction. The department, so now I jump into the work that we did. So it will be based on 2 publications, one in 2019 in soft matter, I will refer it, and another one is this year, 2025, which I will also refer. So I worked with this with two of my students. One is students and another is postdoc. And these are the funding agencies based on this work. So now, okay. So first, let me start with, so the first point is I assume that the audience is mixed. So, I will keep my pace as slow as possible, and you can stop me at any point of time. Okay, so I have nothing to finish. I just want to introduce it all. So first is patterns. Like patterns is everywhere. We can see the patterns everywhere. For example, here the fruit that we know, kiwi, and this is the smell. This book is itself very nice. You can read it. It's a pedagogical book without maths, anything. So you can just introduce to patterns in the biological system. And the main thing is these patterns, what I show in this slide, is a static one. It is not changing over a considerable amount of time. But patterns can change also with time. For example, this one. So I guess, right. So this is chemical oscillations. This is the different chemical reactants are reacting with each other. Okay, they are down-regulated in some reactions, then up-regulated in some other reactions. So there is a chain of reactions, and you see the patterns, which is coming up, going down, then again coming up. So this is a time and space dependent patterns. So earlier one was only space dependent patterns. It is fixed in a time over a considerable amount of time, and this pattern is not like that. They are space dependent, but also time dependent. These 2 gentlemen were, considerably contribute in these systems, chemical oscillations, Prigogine and Alan Turing. They have theories. Now, our point of research, our point of interest is patterns, of course, they are bit different from even from these patterns. So these are time and space dependent, true. But now, if I do an example of this, so this is, I think, you may know, this is a huge stadium, okay, and something is coming, and this fellow here, and all the fellows here, they are watching it, that this thing is coming. Why they are watching? Because they want to jump and go into the pattern, right? It's called Mexican wave. So it depends on, you can easily, figure out the differences between the pattern that we see here and the pattern that we see in the earlier slide. This pattern depends on the information flow, right? That something is coming and I am calculating in my mind that when to jump up to jump into the pattern. So that means this pattern is based on, there is mechanics, of course, but there is a contribution from the information flow throughout the system. Okay. And this is very, very particular for the pattern that we create. We means that the animals, the living organisms, all the living organisms create, they actually can process information and therefore they can contribute to the. This is not there in the inanimate world as far as. So to understand, so our theme is like bottom line of this talk is to understand such pattern, we need to first understand the information flow throughout the clock. Because this seems significantly contributing to the formation of the pattern. So this is also here, I just figure out some examples. So this is word flux that we work on. It's also exchanging information among themselves to create some beautiful patterns. And we can see the density. So in the physics, we call it density waves, okay, that flows from one part from the other part of the flock. So without processing information, without information flow, such kind of pattern seems impossible in the living world. Okay. Now, this is another example. So that the bar flock example is of the scale of, say, kilometers. The Starling flux is of the scale of kilometers, but this is of the scale of, say, micron. Okay. This is the formation of Drosophila, the fruit fly, the morphogenesis of fruit fly. What you are seeing here is the dorsal and ventral part, back and front of the embryo. And all these dots, white dots, are single cells. Now, they form this pattern without knowing what this part is doing to this part. How the information transfer. Do you think this kind of complicated geometry can form? It's impossible, kind of. Right? So, and this thing is happening over time, and it has to, n number of processes are going on in these morphological steps, and every process has to finish at a certain time point such that the other process starts. So there is a, orchestrated motion of the cell, and without information flow, it is not possible. Similarly, not only formation of pattern, but also having complex tasks. For example, these ants, that they are carrying this food to a particular region. Even if we don't understand their language, but still by seeing the video, we can perfectly see that this thing, okay, I should put down. Yeah. So one fellow came and somehow they exchange the information that this particular food element should go in this direction, not in this direction. Right? So they actually, while on the fly, they are exchanging information among themselves and fix the direction. So this complicated task is done by the ants. We also do that. So the main point of showing all this thing is the orchestrated large-scale motion. Okay? Then having complex spatiotemporal pattern formation or cooperative execution of tasks, complex tasks. It is not impossible to without flowing of information. Okay. Now, so then we jump into our primary questions. So we will not claim at the end of the talk that we will have all the answers to these things. These things are quite complicated. But first step is like, what is information? First, to figure out the flow of information, first step is to define information, okay? And then how to quantify it, of course, how to measure it in a given setup. And then we characterize its flow and how the flow affects the mechanics of the flock or some group of people or group of ants, a group of birds. Okay. So these are our interests of these words. So now at this point, whoever has access to experiments, they will jump into experiments. They do the experiments with birds, they may do the experiments with cells in tissues to get the data, to get the collective motion data, and then figure out how can we quantify the experiments. But we do not have the access of experiments. We have expertise in simulation. So we simulate an active system, number of particles who move actively, means with self-propulsion velocity. They have a direction, okay? And with this setup, we try to measure the information. First, after defining it. So this is the main bottom line of the talk. So first, we will simulate a flock, a group of active members, and then we define information. And after defining information, we will see that how this information flows throughout the flock that we simulated. This is the bottom line. Up to this, is the plan clear to everyone? Okay. So then first, how to simulate a number of particles which are active, I would say. Active means they're self-propelling, they're mimicking some actual active elements, birds, cells. But of course, they are a lot more simple. I mean, actual system is really complicated. We will, as physicists always do, they model the system. How they model? They pick up some particular feature of a real system and include them in the model, such that those features are, I would say, like exaggerated in that particular model. Okay. So this is how we simulate. We build up the model. The first is the equation of motion of every particle. What is the equation of how it propels or how it moves? So we go back to Newton. That means that mass times acceleration ddt, which should be force. Okay. Force on a particular particle. What are the forces they are acting? So these are the particles, say, okay, and they are in some medium. Therefore, first, as they are in the medium, what the medium does, if I move through air, I will obviously dissipate, right? Because I will sweat and some heat will be released, right? So this is dissipation. So this is term for dissipation, this term. The friction, and friction causes dissipation. Good. This is the first term. Second term is what? If we are many, we collide with each other. Okay. Going into the cathedral or going into some museum, we always collide. So this is the force of collision. There's nothing active here. Even the passive particles also collide. So this is a collision force. We include it in the model. Then the force which is active, okay, which is not included in the passive systems. Okay. What are these forces? So this force, I took a model which is published in 1995, and in this particular field, it is quite well-known paper. Why? Because first of all, it shows very novel features, physical features, and secondly, it is tested in a living real situations, real flows. And it works not everywhere well, but to some extent it works. Even being very simple. So what is this model? This model is saying that when, say, I want to move according to my neighbors, following my neighbors. Okay? Of course, this is not the only movement possible. I often don't follow my neighbors. Okay, but this is one example, one kind of thing that, okay, this time I'll follow my neighbors. And how to follow my neighbors? I will come. So all my neighbors have some velocities. In my head, I will compute their rough velocities, and then I will compute the average of that velocity also, velocity, magnitude, and direction. And then I will take that direction for the next step. Okay, so this is the basic rule of this model. It is very simple, and this we apply in this we include in our system. And of course, this gentleman actually created this model, Thomas Wiczek. And if I simulate this thing with this active interactions, this following mechanism, then I will get this. In certain parameter space, not in all parameter space, we can get this kind of band formation of these active particles. Okay. And these are the kind of experimental test, you can say, or experimental situations where this model has been tested in case of birds. So my point is that model that we have, we have taken is not actually very off from the real situation. Actually, can mimic some real situations. Then, okay, we put another force, which is we want to confine the system. Why we want to confine the system will become clear to you after some time. But let's say now we have a confinement to the particles, okay, and confining force is this one, F trap. Okay. This is a conservative force. Conservative in the physics language means that I derive the force from a potential. Then, so this is the potential, this blue one, okay? And this flock is, the particles are clustering here. These are the particles here. Now, it is already, you can see the difference of clustering here and clustering there. So the difference is, first of all, you notice the difference in the confinement here and the confinement there. What is the difference? The confinement here is more smooth, right? And the confinement here is more sharp. So first, our simulation shows that if we change our trap in this configuration to this configuration, or vice versa, the self-organization of the particles inside, they also change. Self-organization changing, there is a round cluster here, you see, and there is a particles forming almost a layer, discontinuous layer, but a layer along the boundary of the confinement. So what kind of transition is this? This, in the physics terms, we call first is the weighting-deweighting transition. So weighting-deweighting transition is what? If I have a droplet on the surface, some droplet, depending on the property of the fluid and the surface, it can spread out, or it can be like this. Say if I put a mercury, these mercury drops, they won't spread out. But if I put water, they can. Right? So this is something called weighting-deweighting transition. So some drops weights the surface, some drop doesn't, some fluid. Okay. So here, the fluid is same, but it cannot weight the boundary. But here, the same fluid weights the boundary because it is now spread out. So why this happens? Because I change the softness. This, I would say, the soft potential, and this, I would say, the hard potential. The soft becomes hard, and we see a transition of deweighting to weighting layer.
No, I have a question. So in A, don't you have a minimum, global minimum at the center, and in the other you don't have? Is generated the center point?
I mean, here, right?
Yeah.
So this is almost flat. I mean, the flatness, okay, you can.
It goes smoothly from one to the
Yes,
other.
it's smoothly. I mean, can I have a chalk or something? That is
I think you can get the marker and you have paper.
Oh, where is the marker?
As a marker, I don't know. The paper is there.
Is there a marker? So this flat area, this area, I mean, this is going from here to here continuously. So there's a tan hyperbolic, I would say.
Okay.
So that is the parameter, the sharpness. We can change it, and this is the continuous. It is going from here to here, and we can interchange. So basically, potential is going from this way. I mean, this is the sharp one, and then like this. This is the smooth one. So this function is a tan hyperbolic. You can construct this function with tan hyperbolic. Now, what we see that it's actually, I mean, you can, there is another, so on top of this weighting deweighting transition, there is another kind of transition will happen. This will be clear now. So this is what the particles does in the soft case. This is soft. You can see that this this boundary is hazy, right? And this is what the particle does in the hard case. Now you already, I mean, already mentioned that there is a transition of weighting deweighting one. It is clear here as well, seen from the top. But now there is another. The color means something else. What is this color? The color actually, I paint these particles with something called order parameter, hexatic order parameter, which is defined here. Okay, let's go slow here. So this order actually determines that how many the particles around one particle, how they are arranged. If they form a regular hexagon like this, so all these, they are the nearest neighbors. If they form this structure, a regular hexagon, then this particle, this order parameter of this particle will have 1, the value. Okay. And if they are like deformed, something like this, then it goes down from 1. And if it is completely disordered, then it becomes 0. So this order parameter is a marker of another transition called hexatic, liquid hexatic transition.
I have another question. So the angular noise here in both are the same, right?
Everything else is
confining.
But the confining, yes, exactly. So now you see this red means the highest order parameter value, 1. So all the particles inside, they are hexatically ordered. I mean, not all, but most of them. And here they are not. They are rotating, they are active, so they go to the boundary and they are moving along the boundary. Here is also like that, but here it is being ordered. So there are 2 transitions. One is weighting deweighting transition, that is there, and the other one is the liquid hexatic transition. Order disorder transition is there. Okay. So now these are the properties of active systems that we construct. So we can have, this is a phase. So physicists love to construct a phase diagram.
I have another question.
Yes.
Yeah. Are you doing alignment and attraction, right?
Alignment, no, this force, okay.
Between the parts.
This is WCA, so complete repulsion.
And there is no alignment of the active force.
The Vichek is there.
Okay, that's it.
Vichek is
so
there.
you have alignment.
Yes, alignment and the WCA.
Yes,
and WCA is the passive repulsion. Yeah, exactly. So without this alignment, they only repel each other. So now this is the phase diagram. So phase diagram, in the one axis, I change the hardness of the wall of the trap. Okay, and this is the I change the active force. That's if I go along this axis, the particle will be more and more active. So now we see that there is an ordered region here, as we also see in the configurations, and this is the disordered region if I change the hardness of the boundary. Also, there is another order parameter I didn't mention properly, something called polar order parameter, which is anywhere there. If I have Vichek interactions, then there is a polar, I can change the strength of the noise, the density, and we can get a polar state or a disordered state. So we are in the polar region. So if I don't have anything, no confinement, no interparticle repulsions, the particle will flock in a particular direction. Okay. So we are in a polar state always in this problem. So this is that we already mentioned. This is the weighting deweighting transition. I have already, I think, mentioned it. And now a brief slide for why this order, this hexatic order, the red thing comes up. And it comes up only when I make the boundary soft. This may be clear with this. So this particular, if you in the left hand side, this is the hard boundary case. Okay, and if we will see that particles are rotating along the boundary. You can imagine a boundary there, the boundary of the confinement, and I'm plotting the red one is a typical trajectory of a particle. And you notice the pattern of the trajectory. Okay. Now you notice the pattern of the trajectory in the right hand side, which is the soft case, okay, where the particles are really forming a round cluster, and you will see how a typical trajectory of a particle, of an active particle, looks here and there. The trajectory will look very different. And the difference is, so what we call it here is a kind of Lissajous figure. What is a Lissajous figure? Is like if you have multiple frequency, okay, then you will form such kind of trajectory. Here, how the multiple frequency appear? Here there is a single frequency. Why? This particle is only rotating along the boundary. So there is a frequency attached to the rotation, right? The rate of the rotation. But here, the particles are rotating along the boundary. It is there. That frequency is anywhere there. But there is another frequency by which it is rolling. So it is not only rotating. So this rolling with rotation, this problem is very standard in classical mechanics. If you have a cylinder, then you have this, it can rotate. On top of that, it can roll also on its own axis. So this particular disk, I would say, is not only rotating along the boundary of the confinement, but also rolling around its own axis. And as it is rotating and rolling, you can imagine that this set of particles are always, over time, they are facing the boundary of the confinement over time. These particles, so if this is the boundary, and this is the particle at t is equal to, say, at t1, okay? This particle is here. Now, it rotates along this, but on top of that, it also rolls this. Okay? Therefore, if it goes here, this particle has moved, but some other particle came to the boundary. That is why this cluster is facing the confinement boundary from all directions over time. And that makes this cluster compressed. And you need the compression for building up the hexatic order. Okay? Because particles are coming close to each other, but it cannot cross each other because there is some repulsion, WCA repulsion. Therefore, in 2D, it has to be in a triangular lattice or hexatic lattice. So therefore, we are having this hexatic, liquid to hexatic transition. So this is the feature of this Lissajous figure telling us. Okay. So up to this, we have nice transitions in a confined active system, weighting, deweighting, then hexatic, liquid to hexatic and all. We have phase diagram, fine. And well, now I'm going to introduce something else, but up to now, is there any doubt or anything that very urgent to know? Okay. Then, now we'll start to measure the information flow, at least to set up something by which we can go into the problem of information flow. So now there is a transition we saw in the phase diagram. We will introduce a quench. Quench is what? Like this. So this is the, hardness of the boundary. Here we have the ordered cluster. Here is a disordered cluster. We will instantaneously, we will start from a soft boundary, and then we will make the boundary hard instantaneously. One time, at one time. Then what will happen? The intuition tells that the particles, the cluster, which were round cluster, which were there in the soft case, soft confined case, they will collide. They will bump into the hard wall. Okay. So there will be breaking of the order. The order should go down. Okay. Then, so this is what happens here. So the boundary, the round cluster was there when it was soft. I made the white boundary very hard, and it bumped into it, and then the order goes down. And we see it in the color. Fine. So this is the mechanical response, I would say, mechanical response of the cluster. And this is how we can plot the hexatic order parameter after the quench happens. So it goes down and down. And this is what happens to the polar order parameter. It goes down initially, but then again regains. So this is the mechanical response. But now my question is how the information of the quench, which happened at the boundary, flows throughout the clock, which is now transforming from a hexatic cluster to a liquid cluster. While, on the fly, when this mechanical transitions start happening, during that time, how the information flows. So before that, we need to then quantify what is information. So, I'm starting from the basics here. So now there are, of course, information theory is a well-built theory, and we have a lot of work on this thing. It is an established branch. Let's start from the beginning. So we have something. For the time being, let's forget about the active system and all is happening. Let's focus on some random variable. Okay, some random event is happening X, and so this you can think of as a coin toss, and the outcome is head or tail. Okay, which is your small x I. Now we have this probability of having X in case think of as a coin toss event. Now, if I think of information in this context, I would say, so each and every event has a probability here of some random event. Now, which event will have more information? So intuitive answer is which is least probable. Okay. So, I mean, which happens very rarely. That is why we can extract, when it happens, we can extract more information from that particular event. If some event happens regularly, then it is expected that we know certain things about the event. That means we can't extract much information from that particular event which happens regularly. But if some event happens irregularly, very rarely, then this should contain most information to us. We can extract most information from it. That means the information should go inverse of the probability of that particular event. Less probable, more information. But this is, of course, not the, precise definition of information. This is kind of intuitive. Now, from this definition, we use the log also. This is traditional, and also it maintains the property of additivity of entropy. Okay, why we need to maintain that? That is another story. I'm not going into that. So if I use this kind of 1 by p thing, and then we can get the average information content, which is our kind of known definition of it here. But anyway, we cannot be confined with this. This will not give much in our case. Rather, we have to compare two such random events, X and Y, and how much. So both are random events, but we want to know that how much X is influencing Y, or how much Y is influencing X. This is not clear to us. So the underlying dynamics of X and Y is not clear to us. Okay, somehow we are getting this X and Y. Now we have to figure out that whether X is at all influencing Y or not, or Y is at all influencing X or not. For that, we need to devise a quantity. So first, we define as this is called mutual information or relative entropy, which means that this is a joint probability of X and Y, and this is P of X is called marginal probability of X, which means P of xy integrated over all y, we get Px. Now, say if X and Y are completely independent, say, then this P of xy will become P of X multiplied by P of Y. They are statistically independent events. One are not influencing the other. Then what will happen? This log will become 0. This quantity will become 0. So some event have two events happening, and we are computing this I, and we are getting 0. That means that these two events are independent of each other, statistically independent. They are not influencing each other. And if it is not 0, something else, then we obviously will get, we conclude that they are influencing each other. But this is also not enough for our purpose. Why? Because in our case, there is something happen at the boundary. This is called quench. The particles are going, and those particles which are closer to the boundary, they feel the hardness. They know that now the wall become hard. Okay, we can't move further. And that information should be passed throughout the particles behind them, right? So the amount of information that is known by the front particles, which are closer to the wall, are not same in comparison to the information that is known by the back particles. So therefore, they cannot, how, if X is my front particle, Y is my back particle, how X will influence Y will be not the same as Y influencing X. Right? But this quantity, if you see, if I interchange X and Y, they're same. Correct? So that is not sufficient for our purpose. It is not sufficient for the purpose where the information is actually flowing from one point to the other point. There is a flux of information. Because those particles which are getting information first, they are different from the particles who are getting information later. This thing often happens in the traffic when some accidents or something happen in the front and you don't know what is happening. Then later you can come to know that, okay, something happened in the very front. Yes. So for then, we need to devise some, or we need to use rather, some other quantity which maintains this asymmetry of X and Y. And for that, this paper suggested that there is a quantity which can actually differ between X and Y. I mean, how X influence Y and how Y influencing X, they are different. This can be quantified by a measure called transfer entropy. What is this? Let's see, we have two particles. I'm simplifying the facts. Like now, X is one particle's position at t plus 1. And it is influenced by its own position at t, which is the earlier step. And not only that, it also influenced by its neighbor y at t. So this is the this is the conditional probability of xt plus 1 conditioned to xt and yt. And this is the conditional probability of xt plus 1 at xt. That means we are integrated over all y, all possible y. And then it is averaged over the joint probability distribution, and sum over all x and y. So this quantity is devised by this Thomas Schreiber, also was in PKS, long back, of course. So this quantity says that, okay, it is possible. I mean, it is easy now. Now, if you can interchange x and y, you won't get the same quantity like earlier in case of mutual information. So this quantity actually has a potential to differentiate between x and y according to, I mean, in this information content context. Right? Now, this averaging, I mean, this sum is over all possible x and y. But we want to look at what? We want to look at the information flow within the flock. That means we should not, if in our case, if we want to look at the information flow within the flock, we should not sum over all possible variables, because then the information of having one particle, how it, what is the quantity of the information that is given by one particle to the other is missing, because I have summed over all the particles. Therefore, we have to compute this quantity, there is no doubt about it, but we have to compute it locally. Locally means, okay, this is the full computation. So this is not the local sum. This is the taking the sum over all particles, and it actually shows, this bump actually shows where the collision happened. I mean, at this point the quench happened, and therefore the total, this TE, that is transfer entropy, total global transfer entropy, increases and then again decreases. It shows when the collision happens, when the quench happens, but it cannot show further the information flow. For further, I mean, we have to compute this particular quantity, the same as this, but we have to compute it in a local. Locally means there is a single bird, say here, single particle, okay? And how much this transfer entropy locally, that's why I write it in a small letter, how much information that this particular bird is giving to this one, and how much information this particular bird is giving to this, and how much 5 is giving to 1, how much 4 giving to 1. Say if I, at a certain time point, I have this 2, 3, 4, 5 neighbors of the particle 1. This we can compute, and then we can take an average over all the neighbors. And that average, I say that, okay, this is the information, average information that this particular bird obtained at a particular given time. Now we can do this thing for all particles. So every particles in a flock has certain amount of information, average information from their respective neighbors. Okay. Then, so I paint all the particles with this number, calling this is why this is the number that represents the information of content of single particle at that particular time. Let's see what happens. The same scenario. It goes and then bump into the wall, and we see a front shock kind of movement of this information throughout the flock. And it matches with our intuition that it starts from the boundary, which it should, because there is the quench happened and faced by the front particles. And then slowly, this front moves throughout the flock. Okay. Then we can associate, at least as it is matching with our intuition, we can associate this one as, okay, this is the information that flows from the boundary to the rear end, away from the boundary. So this is the front, which is moving over time. It starts from here, and then it grows, and it goes backwards and longer, and finally it goes down. And so this is the point. This is how we say that, okay, this is the information that flows throughout the flock. It created when we did the quench and faced by the particles which are close to the boundary, and then it flows throughout the flock. And how it flows, that we can measure here. So we can distribute this information, how all the particles are having the information over time. So we can distribute over time, and when the particles actually face the quench, this distribution has a long tail. So the long tail, large tail emerges of when the particle face the collision with the wall, quenched wall, and how the tail grows, it grows ballistically. Okay. So this ballistically means it grows, proportional to time. So that means in this particular case, the information is flowing ballistically. I think this is an important result, but more important is the process. How we land up on this result, the method to quantify the information. Because this result, I'm not claiming it as an universal, that everywhere it will be flowing ballistically or not, that I don't know. Because we haven't tested it, all the real thing, all the other models, stuff like that. But at least there is a process, but the process can be tested. How the information is quantified, how it flows, that is there. And now we can test it for various other models, for various experimental data to show that, to see that whether it is at all working in all other cases, all other possible cases or not, and if it works, then how it works. Whether all cases has this ballistic flow or not, we don't know yet. How the information flows throughout the flock, on which it depends. So these things still remain open. For this particular system, this particular model, it moves ballistically, and this particular quench, I said. Okay. Even we don't know that if I do the reverse quench, for example, if I have the hard boundary first and then make it very soft instantaneously, will this also be ballistic? We don't know. But we can at least now do the measurement, the quantification. Okay. So this thing, again, so these are the references. This is in this reference. And this is the brief conclusion that first conclusion, the first panel is the self-organization, the phase transition that I mentioned. And it's the phase diagram. And the second part is the information flow introduced by the quench. So I think we have, yes, good.